Hello and welcome to this quick video where we're just going to have a look at something called deque. And where you're going to want to implement this is if you're building a queue. Stacks, I found, don't benefit a huge amount from it. And we'll have a quick look at some of that testing in a moment. But just to introduce you to it, it's something you can import from collections in Python. And it's as the highly optimized list. It stands for double-ended queue, where you can do operations on both the front end and the back end very, very efficiently. So let's have a quick peek at how that works. So we'll just run this. This is how you instantiate the deque. You just use this function name. So we're importing deque, and you drop your array into it, or your list into it. And then you can effectively do anything you would do on a normal list or array. But there are certain things that are much more efficient to do on the deque. So let's run this, python deque.py, and you can see that this is what the object looks like. We just have these little brackets with deque and then the array set in there. And don't worry about that, we can handle this just as we would handle anything else. So if we were to append an object onto this, and we don't want to print that out again. We can just append a 6 to the end. We'll save that and run that again. You can see that it just adds a 6 to the end of this list that's within the deque. And if we want to add an element to the front of the list, we use something called append left. So it's as though we're, rather than putting it to the right, to the far end of that list, we're appending it to the left of the list, to the front of the list. This would be equivalent to insert at index 0. We can get rid of both of those actually. Save that and run it again. So you can see that we've just added a 0 at the front of the list. So this is equivalent to insert at index 0. So let's just clear this up. And you can do the same with pop, effectively. So I'll just do both of these. We'll leave this one up and I'll show us both of those. Oh. And you can see that what's happening is when we do test.pop, it just pops the number off the end. So we added, we had the 5 here, and the pop normal just took that number off the end. And you can see that it's printed out the 5 as well, because it printed the popped value. But if we use pop left, we remove the value from the front of the list. And so you can see the 0 that we added here has been popped off the front, and we're just left with 1, 2, 3, and 4. And you can actually do this. They have a version of extend, where that does the normal thing. You can iterate over a list and add those items to the right-hand side of the list, to the end of the list. But there's also extend left, which will allow you to iterate over something and add them to the front of a list as well, and that's very, very powerful. Now I just wanted to show you some of the timing, and it's a really, really rough sort of timing function here, where we just take time.time and the end at time.time and take a runtime. But by doing this over quite a large iteratable or iterated array, we can get a rough idea of how efficient or what kind of gains we can get with this algorithm with the deque. So if I have a quick run through this code, we're making an array and it's got 1 million elements in it, and we're just comparing pop for both of them. So the array, we're going through a normal array, not a deque, and popping off each item from the right hand side until there's nothing left. And in the deque, we're doing exactly the same. We're running through the entire deque, popping off each item, and we'll just get 2 runtimes: the first one for the array, and the first one, and the second one for the deque. So let's run this. Python practice.py, And you can see, and this is what I found in all of my testing with this, that normal functions that you would do on a list, like pop and append, are actually ever so slightly slower with the deque. So that's a negative. That's why I haven't found it useful to use this when working with a stack, when you're just working off that right hand side, so popping and appending items. However, let's now compare this with pop left and what was this one? It'll be insert. No, it won't. It'll be pop at position 0. So that's as though we're popping off the number at the front. So now, rather than working from the right hand side, we're working from the left hand side. So from the beginning of the list, popping items off. And we'll see what happens here. Let's save that. Clear this up. Oh, and I need to drop this down because it took too long. I think it's all right with 100,000. We'll check that and we'll run it. See how long it takes. So instantly you can see that when we're popping items off from the front of the array or the list, it's much slower. 3 seconds to run 100,000. Whereas with the deque, it did it in 18 milliseconds. So it's much faster. And this is where the real power of this comes in for queues, is that we can handle that front of the list as fast as we handle the end of the list as well. And just to sort of drive this home, we'll have a look at the insert as well. So insert 0, and we'll just put some zeros in, and we'll have append left and pop a 0 in there. So all we're doing is, for the range through 100,000, we're adding zeros to both the array and the deque, and we'll see how this performs. So let's just clear this up and run it again. And this is over 100,000 units, so it should be adding 100,000, but from the beginning of the list with the insert function. But with the append left, we're doing exactly the same. We're getting the same result, which is a deque with 100,000 zeros added at the front. And you can see it's a huge difference. The insert function took 25 or almost 26 seconds to add that 100,000 zeros to the front of each list, whereas the append left did it in 25 milliseconds. So much faster. And this is where this little import and use of this data structure can really make your queues a lot more efficient. That object where you add items on at the end, so at the right hand side, but you're also manipulating items at the front, so taking them off from the front. So you can think this would be very useful in things like breadth first search implementations and things like that. I just wanted to also mention, and I'm going to put this link in the description, there's a fantastic article by Louis Chan that looks at the memory efficiency of different data structures, and a deque is incredibly efficient. It's very close to a tuple in its memory efficiency, and much better even than a list. So it's a more efficient implementation with memory considerations as well. Anyway, I hope you enjoyed that one. It's just a quick video, and it's come out of a bit of a natter with a colleague while I've been doing a bit of work, and thought I should probably share it. And it's nice to see the tests as well, because I hear people say that you should use deque as well for a stack. And while it might be true from a memory consideration, I've found that it doesn't really make too much of a difference from a runtime and processor implementation. But anyway, hope you enjoyed. Thank you so much for watching. And if you have comments and corrections to what I've said, or anything you think would be useful to add to this, please feel free to add them below. And I'll see you in the next one. Bye!